Physics, Part 389. Now it's your turn. Using the half-life values given in the table, calculate the fraction of a sample of uranium-238 remaining undecayed after 9.0 into 10 to the power raised to 9 years. Calculate the fraction of a sample of astatine remaining undecayed after 0.30 seconds. Calculate the fraction of a sample of radium-226 that has decayed after 3,200 years. Calculate the fraction of a sample of radon-222 that has decayed after 15.2 days. Mathematical descriptions of the radioactive decay. The activity and the decay constant. As we saw in the dice experiment, increasing number of the dice increases the number of sixes that appear with each throw. Similarly, if we investigate the decay of a sample radioactive material, we find that the greater the number of radioactive nuclei in the sample, the greater the rate of decay. This can be described mathematically as d into n over dt alpha into n. This gives dn over dt is equal to minus alpha into n. N is the number of the undecayed atoms in the sample. dn over dt is the rate at which the number of nuclei in the sample is changing. So minus dn over dt represents the rate of decay. Minus dn over dt is known as the activity A of the source and is measured in becquerels. The activity of the radioactive source is the number of nuclear decays produced per unit time in the source. Activity is measured in the becquerels, BQ, where 1 becquerel is 1 decay per second. So 1 becquerel, BQ, is equal to 1 second. Combining A is equal to minus dn over dt and dn over dt is equal to alpha n. We have A is equal to alpha n. Well, alpha n is a constant proportionality known as the decay constant. It has the units of second, year, and so on. And this decay constant is defined as the probability per unit time that nucleus will undergo decay. This is an important equation because it relates quantity we can measure to a quantity which cannot in practice be determined. And is the number of undecayed nuclei. We shall see later that the decay constant is directly related to the half-life which can be obtained by an experiment. This opens the way to calculating the number of undecayed nuclei in a sample. Trying to count nuclei when they are decaying is similar to counting sheep in a field while some are escaping through a gap in the hedge. We've got an example for you. Calculate the number of phosphorus 32 nuclei in a sample which has an activity of 5.0 into 10 to the power raised to 6 BQ. Decay constant of phosphorus 32, 5.6 into 10 to the power raised to minus 7 per second. And this is how it goes along. It's your turn. Calculate the activity of the following samples of radioactive materials. Number 1, atoms of strontium. Decay constant of strontium is strontium 90 is 8.3 into 10 to the power raised to minus 10 per second. And calculate the 2.0 mg of uranium 238, 0.238 kilogram of uranium. Uranium 238 contains 6.0 into 10 to the power raised to 23 atoms. Decay constant of uranium 238 is 5.0 into 10 to the power raised to minus 13 per second. To solve the equation, you can have it all along with your own scope. However, it is important to know the solutions. In order to find the variation of the time and the number of nuclei remaining, the solution is